In this video, I just want to review some of the applications of first order differential equations that we've looked at already and give you a quick overview of some applications in electric circuits. Most of the details on this topic are left for the text. Our general first order DE in standard form looks like that, where x is our independent variable and y is our dependent variable. And of course, in a typical application, and all the applications that we've looked at so far, and most of the applications that you're likely to see from now on, t is going to be your independent variable representing time, and then you'll have some dependent variable, which I'm leaving as y at this point. That could be almost anything that depends on time. That would be in a first order differential equation in standard form with that notation. Most of the applications that we've looked at so far, and a lot of the applications that we're going to be looking at, are actually autonomous differential equations. So, sorry, there's another one of those crazy check marks. Autonomous in this case meaning that the right-hand side doesn't depend explicitly on time. It only depends on our dependent variable, y, in general. So one of the first applications that we looked at was this, where we assume that we have a population n as a function of time, and we make an assumption that is valid for very simple populations. We assume that the rate of population growth, the derivative on the left-hand side, is proportional to the number in the population. And with that assumption, we've solved this differential equation a couple different ways earlier in the chapter, and we found that we ended up getting essentially a population explosion, is what that equation is saying. Then we also earlier in this chapter looked at a little more realistic population model, which is this one here for logistic growth, where we assume that the number in the population is proportional to the number present, but also proportional to the difference between the population and the carrying capacity, K. And that was quite a bit more involved to analyze, either qualitatively or exactly, but we ended up coming up with that expression for the exact solution for logistic growth. And hopefully you will recall that in both of those, in the simple population problem here and in the logistic growth problem here, both of those are autonomous differential equations, and we were able to study those qualitatively by thinking about equilibrium points and the stability of equilibrium points. The first one had one equilibrium point, and the second one has two. We also looked at Newton's law of cooling, which is this differential equation earlier in the chapter. Again, we're making an assumption that may or may not be true, and then we see what happens based on that assumption. In this case, with Newton's law of cooling, we're assuming that the rate of change of the temperature is negatively proportional to the difference between the temperature and the temperature of the surrounding medium, which is assumed to be constant. And based on that assumption, we derived that expression for the exact solution. And again, we talked about the connections between the exact solution and again, our differential equation is autonomous, so we were able to think about that also qualitatively. The differential equation here, this right-hand side, has one equilibrium at t equals t sub m, and we saw that that was a stable equilibrium. So those are some of the important applications that we've looked at already in this chapter. Very important class of applications that we study in this course are things based on Newton's second law in mechanics. There's a quick review of the notation here that we use in connection with this topic. So Newton's second law is essentially, the short version is F equals ma, force equals mass times acceleration. Hopefully you have encountered some version of that law somewhere earlier in your studies, either in college or high school. So that would be a fairly general statement of Newton's second law, which would give us a second order differential equation, which is a more complicated topic, and we're going to be studying a lot more about second order differential equations later in the course. So for now, we restrict our attention to a situation where the force only depends on the time and the velocity. In that case, Newton's second law looks like that. And really, most of the time so far in this chapter, you're going to end up with an autonomous differential equation. So something like that, where your force really only depends on the velocity. Here again, we're making an assumption when our differential equation is basically a model based on assumptions that we may or may not be able to verify experimentally, and based on those assumptions, we see what happens with our solution. The simplest possible thing we can assume about an external force is that there is no external force. In that case, Newton's second law looks like this if there's no external force. So the time derivative of the velocity is 0, which means the velocity must just be equal to v naught. It just must have that constant value. Is if there's no external force, then the velocity is just constant. A little more interesting situation is when we have a constant gravitational pull on our object. The main application of this would be to studying motion near the surface of the Earth, although there are many other applications of constant acceleration problems. This is the one that you're most likely to encounter in this course. If you're only dealing with that kind of force, and if there's no other forces going on, then that would be your differential equation. In other words, v dot, the time derivative of v would be negative g. We've chosen negative g, the sign convention, to be down with the idea in mind. We're thinking about the x direction as being up and then acceleration being down for motion near the surface of the Earth. Of course, that's easy to integrate with respect to time, and we get that expression for the velocity by integrating that differential equation. There is a much more detailed discussion about electric circuits in the text, and I'm only going to hit a couple of highlights here. Here again, for the more general problem, we're going to end up dealing with second order differential equations, which will be studied in chapter 2. So for now, we're restricting our attention to an LR circuit, a circuit that contains only an inductor and a resistor, and possibly an EMF, or an RC circuit, a circuit that contains only a resistor and a capacitor, but no inductor. And again, there's a much more detailed discussion about all of this in the text. Personally, the way I teach my course, I do not expect students to necessarily remember these formulas, but they should be comfortable with them. The engineering folks probably will have seen these formulas and gotten comfortable with them, but that may or may not be the case for the other students in my class. So I do expect people to remember anything that we ever talk about in connection with mechanics. I consider that more fundamental than these electric circuits formulas. In any case, for these problems, for these first order differential equations, they both are going to end up being autonomous if your EMF E turns out to be a constant. And when that happens, the first one, we can think of it that way. The second one, we can think of it that way. Each of those then is a first order linear autonomous differential equation, and each of them then will have one equilibrium point, and that would be one way to think about the solution of each of those equations qualitatively, by thinking about the stability of the equilibrium point.